Dear students, welcome to my channel. Topic of this video is RSA algorithm part 1. RSA cryptographic algorithm was invented in 1977 by three researchers, Ron Rivest, Adi Shamir, and Leonard Adleman. The algorithm is named after their initial Rivest, Shamir, and Adleman. RSA is asymmetric encryption algorithm that uses pair of keys, a public key for encryption and a private key for decryption, which enables the secure communication over untrusted network. The security of RSA relies on the computational difficulty for factoring a large prime numbers, as deriving a private key from the public key requires factoring of the product of two large prime numbers. So I have explained this already in my previous video. RSA supports both encryption and digital signature, which allows not only secure data transmission but also authentication and integrity verification through signing and verification process. Key generation in RSA involves the basic step: select two large prime numbers P and Q, compute their product, and choose a public key which is co-prime to Euler-Torsson function phi of n, followed by deriving the private exponent d. So when we will take the key generation and encryption decryption, then these steps will be clear. Despite its computational overhead, the RSA remains widely used in SSL TLS, digital certificate, and secure email, that is pretty good privacy, and blockchain technology to proven its security and versatility. RSA is vulnerable to quantum computing attack, which make potentially insecure in post-quantum era unless combined with the quantum resistant cryptographic techniques. RSA uses modular exponentiation for encryption and decryption, which is expressed as, so for encryption, that is to make a ciphertext from the plain text, we are using C is equal to m raised to e mod n, where e is the public key of the receiver and m is equal to c raised to d mod n, where decryption takes place to get the plain text and where d is nothing but the private key of the receiver. RSA is divided into three main stages: key generation, encryption, and decryption. Key generation. The first step is to select the two large prime numbers, compute n, p and q. So now key generation takes place. For example, when A wants to communicate to B or A wants to send an encrypted message to B, so at the B, the key generation step takes place. So B chooses the two large prime numbers P and Q. It computes n equal to P into Q. Then it computes the phi of n. Now phi of n is very easy because P and Q we know, so they are the prime number. So phi of n according to Euler-Torsson function is P minus 1 into Q minus 1. So it is very easy to calculate the phi of n if we know the factorization. But if we don't know the factorization of P and Q, at that time it is very difficult to calculate the phi of n. So that is nothing but the hardness or the trapdoor function for the RSA, that it is very difficult to detect or to guess for the private key if we don't know this P and Q number. Now encryption. So once the key generation takes place, so public parameters are n and the e. E is nothing but the public key of the receiver. So it will send n and that public key to the sender. Now encryption. Now here sender will take a message and it will encrypt using the public key of the receiver. Then E chooses by key generation, that is at the receiver side, but in such a way that E and phi of n, they are relatively co-prime to each other. So when we will solve the example, it will get clear. Decryption. Then when the message reach to the receiver, then it will do the decryption using the private key, that is nothing but D key, which is nothing but the, and D and E are modular multiplicative inverse, that is D into E mod of phi of n equal to 1 or D into E congruent to 1 mod phi of n. Now here the public parameters are E and n, where n is nothing but the multiplication of P and Q. So when we are sending from receiver to sender this n parameter, at that time only n is visible, P and Q are not visible. Then public key is nothing but the E of the receiver. Now using this key and this n value, it will encrypt the message, and at the receiver side, receiver decrypt the message using the private key, and at that time he knows P and Q. So at that time that is nothing but this P and Q are known to only the receiver who is generating the private key and public key pair when we want to make the communication between A to B. Now we will see the problem. P equal to 3, Q equal to 11, E equal to 3, M equal to 8. Apply the RSA algorithm and encrypt and decrypt this plain text. So initially do the encryption and after that do the decryption. So first step, we will calculate the n. N is equal to P into Q, that is nothing but 3 into 11 is equal to 33. Phi of n, 3 minus 1, this is a prime, so 3 minus 1, 11 is prime, so the phi of n of prime numbers is nothing but n minus 1. So 3 minus 1 into 11 minus 1, which is equal to 20. Now we choose the public key E equal to 3. Now 3 and 20, they are co-prime to each other. So this is the valid public key. Now our input text is 8. Now we calculate the D. So we can do the encryption, but before encryption, decryption, we calculate the D. D is nothing but the private key of that receiver. Now D into E is equal congruent to 1 mod phi of n, or if we take this E this side, it will becomes the E inverse. So that is nothing but D congruent to E inverse mod of phi of n. Here phi of n is here, phi of n. Now E is equal to 3 and this n is equal to 20. So we require to calculate this multiplicative inverse. So we require to use extended Euclidean algorithm. So we require to calculate 3 and 20 extended. So in my previous video, I already explained how to apply the extended Euclidean. So this is the first step. For example, I will explain for this example. 20 we will write 3 6 are 18 plus 2. This 3 will come here. 3 is equal 3. This 3 will come here and this 2 will come here. 2 1s are 2 plus 1 3. Then this 2 will come here and this 1 is come here. 1 into 2 is 2 plus 0. After that we will take the 20 minus 3 of 6 equal to 2 and 3 minus 2 of 1 equal to 1. So here the whatever the value which are not in a bracket, they are nothing but the variable, and the bracket value, they are nothing but the coefficient. Now we will take back substitution process. So first we will take this equation, then we will substitute. Now 3 minus 2, 3, 2, 1, they are the variables, and this is nothing but the coefficient. Now we see this variable is present here. So this 2 is substituted by 20 minus 3, 6. So we will substitute, we will do the operation, and we are getting the values. So our calculation is with respect to 3 and 20, say 20. So with respect to 3 we are getting the 7, and which is positive. So multiplicative inverse. Now our E is 3 and D is 7. 7 3s are 21, which is congruent to 1 mod 20. So when 21 minus 1 is divisible by 20. So they are satisfying the condition. Now we will see the encryption and decryption. Now when receiver calculates the N and when the receiver calculates the E, it will send these two parameters to the sender. Now sender will encrypt the message. So here sender will encrypt the message by using the formula C is equal to M raised to E mod N. Now M is 8, E is 3, 8 raised to 3 mod 33. Now here we can solve by directly because the exponent is very small. But if we want to use square and multiply algorithm, so in my 3 to 4 videos I have already explained how to apply the square and multiply algorithm. So we can apply the square and multiply algorithm to calculate this 8 raised to 3 mod 33. So we get the cipher text as 17. Now we want to do the decryption. Now decryption, the formula is same, only this E is replaced by D, this M is replaced by C, and this C is replaced by M, because it is a decryption process. So for decryption, C raised to D mod N is 33, C is 17 cipher text, and D is our 7. So by this way we can calculate. Now here we are calculating with the square and multiply algorithm. That is initially z equal to 1, then we convert this 7 into the binary take from MSB to LSB. When 1 is there, we perform both operation, that is square and multiply, and when 0 is there, we perform only the square operation. So by this way we are getting the value 8. But for decryption, we can solve using the Chinese remainder theorem if this number is very large. So when this number is very large, it is very difficult to solve. So at that time, and this number is very large, and even at the same time, if this exponent is very large, at that time it is very difficult to solve by the even directly by the square and multiply algorithm. So at that time we can use the Chinese remainder theorem. So Chinese remainder theorem is only takes place at the decryption, because at the decryption they know only the value of P and Q, because sender will never know the P and Q value. Sender will know only the N value. But at the decryption, at the receiver side, decryption takes place with the private key, and that process we can simplify using the Chinese remainder theorem. So either we can solve by this way, or if this number is large or this number is large, we can go by the Chinese remainder theorem. So here for Chinese remainder theorem, it is the dp is equal to d mod p minus 1. Now our d is nothing but the private key, that is nothing but 7, and p is nothing but, now here we divide the number, that number is our 77. Our number is 3 into 11. So p is 3 and this is 11. Now d is 7 and number is 3. 3 minus 1 is 2. So 7 mod 2, the remainder will come. So dp is 1. Now dq is equal to d mod q minus 1. D is our 7 and q is nothing but 11. 11 minus 1 is 10. So 7 mod 7. So here we are reducing this problem like this by using Chinese remainder theorem. Now we'll write c raised to dp mod p. Now c is nothing but 17 and dp calculated 1 mod 3. So 17 mod 3 we can easily calculate. The answer is 2. And next is mq is equal to c raised to dq mod q. Now mq is equal to 17 raised to c is our 17. Now dq comes 7 mod 11. Now to solve this, as this value is small, so we can easily do the calculation first. So by square and multiply algorithm, we can calculate 17 raised to 7 mod 11, which comes as a 8. So we are getting the two equations. So first, in Chinese remainder theorem, we at the receiver side we know the p and q. So first we calculate the dp, which is nothing but d mod p minus 1. Then we calculate the dq, which is nothing but d mod q minus 1. Then we write the equation that mp is equal to c raised to dp mod p and mq is equal to c raised to dq mod q. Now we are getting this equation, that is mp is 2 and mq is 8. Now here we can write down the equation mp is equal to 2 mod 3, because for the first the p is 3 and mq is 8 mod 11. So this 2 mod 3 and 8 mod 11, we'll write down this equation. I have already published the video on Chinese remainder theorem, so to better understand, you first watch that video. Now here we calculate the capital M, which is nothing but 3 into 11. After that we calculate M1 and we calculate the M2. Now here we will take M inverse, that is y1 is equal to 11 inverse mod of 3 and y2 is equal to 3 inverse mod of 11. Or otherwise we can write down 11 y1 is equal to 1 mod 3 and 3 y2 is equal to 1 mod 11. Now we can apply the extended algorithm. So we can apply the extended algorithm 11 3 to get this and 3 11 to get this. So by applying the extended GCD we get the answer. So here I have explained for this example GCD 11 3. We will write down this, then we will write down the equation in a different format, and then we use the back substitution. So these steps are basic, and by this way, now here our first equation is 11y mod 33. So we require to calculate 11x plus 3y. Now here we can see that for this equation 11, our value is what? Minus 1, and we don't want minus 1. So we have to, so we take, that is Now see this equation 11y1 with respect to mod 3. So we will take this as value as positive. So minus 1 in come. So 3 minus 1 equal to 2. And for y2, this is with respect to 3 and 11. So mod 11 is there. So y2 is with respect to 3. So with respect to 3, our value already positive comes, which is nothing but 4. So in this way we calculate the m1 inverse and m2 inverse. And after that we can apply this is Chinese remainder formula. That is nothing but a1. So these are our basic equation. That is nothing but 2. These 2. Then inverse we calculate 11. M1 calculate 11. And here y1 calculate 2. For this a2 is nothing but a. Then we calculate, that is nothing but m2, which is equal to 3. And y2 value is 4. So we multiply and then add, and we take the mod with respect to capital M, that is nothing but 11 into 3, 33. We are getting the answer 8. So in this way we can solve the problem using the Chinese remainder theorem if this value is very large as well as this exponent is very large. So better way is to go for the using the Chinese remainder theorem for the decryption. So this is all about the RSA algorithm. So these are the references. Now this is the part 1 video for the RSA. In the next video I am going to explain 3 more examples on RSA. Thank you.